listening to the entire talk. That's always good.
I guess we'll start because we will have to start. We said we start at 1. And I'll take another registration so we know who are here from the students.
That's the same, whatever country you're in.
Yeah, it is the same. It is always the same. Okay, for those who came in time, thank you very much. And for those who join us later, they are welcome. But still, a good thank you for those who came in time. So thank you very much. And now we will start our talks after the break, and we start with Dr. Jaap Boender. How do you pronounce your name? Boender. And you don't pronounce the D, huh?
Boender.
Boender.
I don't. You're supposed to.
You don't, so Boender.
Boender.
Okay, so, and Jaap is or Jaap or Jaap? Jaap. Where are you from?
The Netherlands originally.
Netherlands, okay. But he's representing Middlesex for us, Middlesex University, so welcome to Cairo University. And Professor Jaap will be talking about introduction to theorem proving with COC. Okay.
Thank you for the intro. So
I think they will need the mic.
We need the mic.
It's very.
Is this? Yes. All right.
It is, yes, I think.
Okay.
Yeah.
I'll just hold this in front. So I'm Jaap Boender, senior lecturer in Foundation of Computing Science at Middlesex. Originally from the Netherlands, but I've been living in London for a while now, so I think I'm starting to become slightly more British every day.
Please raise your voice, it's not that clear.
Okay. So what I'd like to talk about basically is introduction to theorem proving with COC, and especially software verification. So what is this? So basically what are we going to talk about? A bit of theory and then a lot of practice. So I'll explain a bit about what COC is, what you can do with it, what the theory behind it is, and then we'll have a bit of demo just so you can form an idea on what it is that I'm talking about. So just very quickly about software verification. So generally what you do, of course, when you implement any kind of software system, you have a specification, you make some sort of implementation of that specification, and then hopefully the implementation actually matches the specification, ideally. So software verification is nothing more than actually using formal methods, mathematical logic to check whether the implementation matches the specification. So you can be slightly more confident. So the big caveat here is that it's not 100% reliable. So yes, you can you can write your specification, you can make your implementation, and you can use theorem provers such as COC to check whether they match. But of course, that still doesn't completely preclude that there might be bugs. It definitely can make you a lot more confident, but you still have to write a proper specification. If your specification doesn't include the things that you want to check for, then you can check whether the implementation matches the specification. It still won't remove all the bugs, and also the theorem prover itself might be buggy. So it is a way to be more confident. It's not the absolute truth. This is not something that will work in all cases and will just tell you, yes, this program will never have a bug ever. It would be nice if that were possible, but obviously this being an imperfect world, that's not the case. So COC, the program. So there's a whole bit. So it's a formal proof management system. It provides a formal language. So I've put the important bits of this definition in red, which I think you can't actually see on the screen. So the important words here are proof management system. So COC is a way to manage mathematical proofs. So mathematical logic, mathematical proofs. It's a way to manage those, so to make proofs, to check proofs, that kind of thing. So it provides a formal language. So it is a formal. It's actually a complete programming language you can use to manage proofs. To write mathematical definitions, so theorems, lemmas, all that kind of thing, executable algorithms, so it is actually a fully fledged programming language. You can write your algorithms in Coq. And theorems, so together with an environment for semi-interactive, so it's not automatic, it actually, during the development of your proof, you will be helping the proof along, of machine-checked proof. So what the prover can, it can't make your proof for you, that's why it's semi-interactive. What it can do is check your proof and figure out whether your proof is actually correct. And then it goes on about typical applications, so I've got a slide on that later on, so we'll skip that for a moment. Also, yeah, so the last application is also interesting for teaching. So a few applications, yeah.
What do you mean by proof management?
So proof management is basically, so when you take a mathematical theorem, so let's go for the four-color theorem, for example. So what Coq allows you to do is it allows you to state that theorem in some way, so you write the definition, and then to use, and this will become clearer on later in the demo I think, but it allows you to use ways of specifying a proof for that, that particular theorem. And then it will, at the end, tell you, okay, you've now proved that the proof is correct. So it will tell you, okay, this is a valid proof of that particular theorem. That's basically. So yeah, the mathematics you can prove it. So this was its first application, where it's actually formally proving mathematics, so taking actual proofs that mathematicians have worked out and checking whether these are correct, because if you can, of course, you get things like peer review and papers, but it would be nice to have proofs actually checked by a machine. So things like, so the first and most famous application was the four-color theorem. Every planar graph can be colored with four different colors. This is Georges Gontier. That was basically the thing that put formal theorem proving on the map. There were a few people from Nijmegen who did the fundamental theorem of algebra, which gave rise to a whole library of kind of mathematical functions. Somebody did some work on disjoint set data structure correctness. The latest thing is the Phi-Thompson odd order theory, which is a big result from group theory. So this was actually the anecdote here is that Gontier talked to some mathematician friends of his, said, "Oh yeah, I've proved the four-color theorem," and they said, "Yeah, that's not really impressive. That's already been done by computers." So they weren't really impressed, and then Gontier said, "Okay, so what theorem would really impress you if I managed to prove this in Coq?" And then they said, "Well, go for the order theorem. That's really a complicated proof. It's really big. It's interesting. So go for that." And I think about 10 years later, a huge international research project actually managed to prove that. So just to show that impressive results sometimes come from small beginnings. And also, so this is more on the mathematical side. When you talk about the formal verification of software, so there's now something called CompCert, which is a C compiler, which actually has been formally verified. So for a C compiler, what you want to check is whether the output is semantically equivalent to the input, in the sense that you put in a C program that does something. The assembly you get out the other end should do the same thing, right? That's what the compiler. So they've actually managed to put that into a specification, and now formally verified that that compiler actually verifies that specification. So CompCert is a formally verified compiler for, well, a large subset of C, if I'm not mistaken. So how does this work? So just a bit of terminology. So it's based on the calculus of inductive construction, which is basically a system of logic. So it's a logic, and the most important bit here is constructions. So it's based on constructive logic, which means that, for example, if you have so it's proof, something can only be proven if it's actually constructed. So you don't have, and I don't know how well your background in logic is, you don't have the law of the excluded middle, basically. So the law of the excluded middle states that a proposition has to be true or it has not to be true. There's no third option. Constructive mathematics doesn't have that excluded middle, so it can be true that propositions are neither true nor false. And for example, one of the famous examples of this is unsolved mathematical problems. For example, P is NP, P equals NP. We don't know whether that's true because that hasn't been proven, but we don't know whether it's not true either because that hasn't been proven. So in constructive mathematics, it basically says, well, that kind of problems are taken care of. It says here the calculus of indictive constructions. Of course, that's supposed to be inductive construction, so there's a whole system to deal with induction. So it's basically, so Galila is the main bit of code, which is a complete functional programming language, which is very richly typed for reasons we'll go into in a minute. And it also contains a complete higher order logic. So basically, the way you work in Coq is basically that you implement a program and then you try to prove some properties of that program, basically that it verifies your specification. So you can actually more or less implement your specification and your implementation in the same language and then check whether they match up. There's a vernacular as well, which is basically, yeah.
That was to move
Okay. That's all right. Yeah. So just so you can see the slides. So yeah, vernacular basically is the language that you use for define. So the sort of the command language, let's say, in a sense, this bit's definition, this bit's proof, this bit is a theorem, and so on and so forth. And there's also a tactic language, which is kind of a way of automating certain proofs. So sometimes you have a proof, for example, where you have to prove a lot of things that are slightly different. They're most of them things slightly different. So a tactic language, for example, you can loop that or say, okay, repeat this particular thing 16 times, that kind of thing. So it's sort of an automation. Again, this will probably become a lot clearer when I actually get to the demo, because then you'll see how it works. Yeah.
Regarding the automation,
Yeah.
Is this somehow related to tools like Jenkins, like Chef Puppet, which are automating a certain execution of scripts? Is this related or is it
No, not really. So yeah, Jenkins is exactly it's an automated build system, so it compiles things. This is related to actually sort of checking the function of the program in a sense. So making sure that it does what it's supposed to do. So that it's completely orthogonal to.
So it can belong to the set of automating tools for testing automation, like for example, things like that.
Well, the thing with Coq is that it's very much about interactive theorem proving. So the thing with since Gödel, we know that sort of you can't prove. It's not that there will always be times when you can't do automated proofs. So automated proofs of math, it's usually possible for a very small subset of logic, but anything more complicated, you actually need to have user input. So Coq, one of the big advantages of Coq is in fact that it isn't automatic, so that it allows you to prove more things, but you do need constant user input. So automating this would actually be fairly difficult, I would say. That's the whole point. Makes sense.
If we're trying to compare Coq Z.
Yeah, that's where it starts. That's where you start getting into the. I mean, I'm not. I know Z by name. I don't know sort of where it's.
Z is a specification language. It doesn't have a proof. But it is a specification.
Exactly. So what you can see Coq then as a sort of a specification language.
Does it integrate or kind of work with Z?
No, I don't think so. It has its own specification language basically. So it fulfills the same function. I don't think there's actually a way to bridge the two. Well, you could, I imagine, actually make a translator between the two. So, as far as I know, there's no specific thing. Oh yeah, so very quickly, because when you talk about things like formal verification and specification, the question is, of course, so this tool tells me that I need to, this tool now tells me that it's okay, that's somehow my specification matches my permission. So it's telling me it's okay, but how can I trust that particular proposition? How can I trust this tool that tells me everything's okay? So there are basically 5 things that sort of where it can go wrong. So the first thing you need to trust is basically the calculus and inductive construction, so the theory, the logical theory that Coq uses. This has been around for 20, 30 years. It's been, people regularly publish about this, so you're probably reasonably safe there. There are about 10,000 lines of code that you need to trust. So that's the Coq kernel implementation, and why you only need to trust this, we'll get into in a minute. But there is a very small core. Basically, the only bit of Coq that you need to trust is the type checker. We'll go into the reasons for this in a minute. The OCaml compiler, so Coq itself is written in OCaml. So obviously, if there are bugs in the OCaml compiler that produce wrong code, that might be a problem. Again, the OCaml compiler sees pretty heavy use, so it's probably gotten all of the major bugs out by now, but you never know. Your hardware, you may have hardware problems that end up having problems. And of course, you need to trust yourself, as I said earlier. If your specification doesn't actually match what you're trying to check, so you're designing a subway system and you forget to specify that two trains can't be in the same place at the same time, yeah, then obviously you may have problems. So it's so that's also a part you need to trust. So, and it does sometimes happen that you find bugs. So the most amusing one was very recently. So, but it also to give you an idea of how obscure these bugs actually are. So they managed to prove false, which is basically false is by definition a proposition that can never be proven. So if you manage to prove false, something is definitely going wrong. They managed to, so there's something called variant types, which is basically sum types from typing. And they used a bitmap to, bit mask to use for all the different variants that are possible. So I think they had 1 byte identifier. So and then you had 256 possible variants. So at some point somebody decided to define a type with 257 variants, and there was basically an overflow in the bit mask, and they managed to use that to prove false. So it is possible to find bugs in your theorem prover. It is also probably, if you actually use it for normal things rather than actually going to actually look for error, you probably won't run into them. So these bugs are really obscure. So generally, this stuff is pretty trustworthy. There was also something that you can, which is an old bug where you could, so Coq has a plugin mechanism, you could introduce, so well-meaning, so you could introduce plugins that try to subvert the type checker, but that's something that you can, if you really check important stuff, you can just disable all plugins, and that's something that doesn't really lead to trouble. So yeah, the Coq stuff. So this, I'm going to skip this very quickly. So the main thing here is to see that Coq, it basically the approach of Coq towards proving is proofs are programs, proofs as programs. So how does this work? Well, it's called the Corey-Howard isomorphism. So when you do software engineering, of course, we all know about programs and type. So a type can be inhabited by a program. A program has a certain type. Coq actually does the same thing for proofs and propositions. So a proposition can basically be seen as a type, a proof can be seen as a program. So if I can write a certain, if I can write a program that has a certain type, then I can also, then that's equivalent to having a proof of a certain proposition. So for example, if I have a proposition A and a proposition B, and then I find their equivalent types. If I can write a function that goes from A to B, then that actually is a proof of the proposition A implies B. So basically, yes, you can. So every type has so propositions are implemented as types. Every proposition, every mathematical proposition has its equivalent type. Then proving that specific proposition is equivalent to writing a program that takes a value of the specific type and returns a value of what you're trying to prove. So so this is, and especially when you talk about software proving, it's very interesting how this works, because basically programming and writing proofs are now the same thing, which makes it very easy when you're doing software verification. Basically, programming will already do that, so you don't actually have to know a lot about logic to just start working with this. It is just programming. So That's a big, and yeah, this whole programs as proofs interpretation is called the Curry-Howard isomorphism. And this is basically the thing in which Koch differs from quite a lot of other theorem provers, such as Isabelle, which uses a slightly different, which uses a radically different approach actually. And the thing here is, so the point here is that type checking generally is decidable. So type checking whether a program has a certain, whether a program has a certain type, that's decidable. So you can decide whether a program is a certain type, so you can check whether a proof is valid for a certain proposition. That can be done automatically, type checking is. However, type inference, the other way around, so going from a type to a program, that's absolutely not decidable. Generally, that's different. So this is where you go into the automation. If you try to find a program that implements a certain type, that's not decidable, so that's where the interactivity comes in. So actually making the proof, that's still something that you'll have to do yourself, though there are bits and pieces that can be automated.
Excuse me?
Yeah.
What exactly do you mean by type?
So well, when you have a program and a type, so a function going from integer to integer, something like that. So when you take a program, it generally has a certain input type and an output type.
So you mean data?
Yeah, data type, exactly. So the type of a program is basically what input does it take, what output does it give you. That's sort of from when we talk about type theory. That's what we're talking. So these types then. So in every proposition, every mathematical proposition can be represented by a specific data type. So we'll see that in a moment. But yeah, so this is the point. So it works in one direction, it doesn't work in the other direction, or at least you need some interactivity. Okay, as a random. So Koch as a programming language is a pretty good programming language in itself. It's got a really powerful module system. So it's even it doesn't really actually developing proper programs in Koch, probably because it doesn't have a compiler and it's not really optimized for that. But you can write programs. One of the nice things that it can do is actually it can. So if you write programming in Koch language, it does actually do code extraction. So you can take your Koch program and then extract it, which basically would mean translate it to a slightly more useful programming language, such as OCaml or Haskell. Yeah.
Would you please read more about the differences between Isabelle and Koch?
Okay.
If there's something that Isabelle does not do.
Okay, well let's very quickly.
You have a chance.
Yeah, no, that's fine. We've got time, I think. Not sure how far along I am, but sorry.
22 minutes.
22 minutes. Okay. So in a nutshell, the Isabelle and Koch, they do more or less the same thing. I mean, it's all about so Isabelle as well is about interactive theorem proving. So in general, they're big. You can do the same things in Koch as you do in Isabelle. They're slightly optimized for different things, but the basic function is the same. The main difference between Isabelle and in Koch is how they actually represent mathematical proofs. So in Koch, you really have this proofs as programs approach, which means that actually verifying a Koch theorem, you can, if you don't trust the Koch kernel implementation, you can actually write your own, because you basically just need to write a type checker, which granted isn't the easiest thing in the world to do, but you could do that if you wanted to. So Isabelle uses a slightly different, so this is what's called an LCF style they have an abstract data type that represents mathematical proofs, and the data type is constructed in such a way that if you construct your proof according to this data type, it's impossible to create something that is not logically true. So the bit that you need to trust there is really you need to trust this particular data type, and it's quite a lot more difficult to write an independent verifier, because you actually need to have this whole data type implementation. That being said, the bit of code that actually does the data type and the verification is very small, so the amount of code that you need to trust is still not enormous. But that's the sort of the main difference from a technical point of view. So that's basically all I've got in the way of slides. So let's. And now I'm really going to have a problem because I basically need 3 hands. So let's have a quick look at just start to put it here. I forget I'm still. So this is let's make that slightly larger. Good luck. Can we see this at the back as well, or do I need to enlarge it a bit more?
Lights. Maar wat bedoel je?
The lights. Okay. All right. So these are just. This is just basically how you do mathematics in English. Just to give you a very simple example. So I just define two propositions, A and B. Nobody knows what they are. Just they're general sort of propositions. So now if I want to, so I then basically tell Coq to run that definition. And now I define my theorem simple as A implies A, which is very obviously true. So I find that, and now you can see here on the right that basically Coq is now going to proof mode. So I've now got one sub goal. So I need to prove A implies A. Okay, so start the proof. Now the first thing I'm going to do, so A implies A, well basically this is obviously entirely trivial, but you'll notice that there's a big line in my proof mode, so just below the one circle you'll see a line. Basically everything above the line are things I know, so hypotheses I can use. Everything below the line are things I still need to prove. So A implies A basically means that if I know A, I can prove A. That's what I do. So the first thing I'm just going to introduce, because basically I will need to prove that if I know A, I also know A. So I'm going to introduce my proposition. So you'll see that now I've created a hypothesis which is called A, and I need to prove A. Now this is obviously even more trivial. I don't know if there are gradations in triviality, but yeah. So now I can just say, well, I'm trying to prove something that I know is a hypothesis, so I can just say, I know A assumption. And now no more subgoals. It's I've created my proof, so I can just go QED, and now you'll see that simple is defined. And we can actually look at the proof term. Because we'll see that simple is a function that takes an argument h of type A and returns a type h. So it's basically, simple is the identity function. A proof of A implies A is basically a function that turns A into A, which is the function that doesn't do anything, the identity function that returns its input. So you can see that that's actually the exact function that it does. This function has type A of A. So this is how the proofs as program type works. Basically, what I do is I create, because if I try to print simple, I think I can do that here as well. So if I start to print simple at the beginning of the proof, that's not possible yet. But basically, what this proof is doing, it's basically, I'm using these commands, they're called tactics, so intros and assumption. I'm basically using these to construct a function that basically turns my input proposition, the type of input proposition, into the output type. So and this works for, so you can, there are different tactics as well. So for example, if I try to prove that A implies B implies A and B, again, I can introduce my hypothesis, and now I've got something that's A and B. So now I need to basically, prove two things, because I need to prove A and B. I need to prove A and B separately. So that's what the split tactic is for. Basically, we'll see now that I've got two sub-goals, one which is A and one which is B. And then again, I can either use the assumption tactic, saying, okay, this is somewhere in my hypothesis. I can also actually point to the exact hypothesis I'm using, so in this case, exact H. And then my second goal is at H0, no more sub-goals. So if you look at the If you look at also simple subterm, so we notice that if you look at the end is actually basically represented by a data type which is called conj, from conjunction. So the only thing this proof actually does is it actually creates this data type. So if you look at, I think it's called, if you look at the end, the way the end is defined as a data type. I don't know if you can see that or if it's behind the lectern. I don't think I can actually move this up very much. But the way, so the end is basically defined as a data type which has one constructor. So end is a data type which takes two parameters, the two bits that I'm actually trying to end together, so the two elementary propositions that are the arguments of the end. And there's one constructor for this end data type, so the conj constructor. So if I want to make, so the type for the end is the end type, the way to actually make it is the conj constructor, and my program is also simple. All it does, it actually takes the two arguments, so it takes h of type A and h0 of type B, and it uses the conj constructor to turn those two into an end type, which is how we've actually created the. So that's how you create this particular logical end. Well, there's there, so you can also, the same thing works for the OR. So when you look at, so the OR type, actually, if we look at that. The OR has two constructors, because there are two ways to construct A or B. Because for the end, basically, if I have the proposition A and I have if I have a type, if I have a proof for A and if I have a proof for B, I can extend that to a proof for A and B. However, when you talk about the OR, there are two ways to do that. So if I have A or B, either I can go from A to A or B, or I can go from B to A or B. Well, that's exactly what happens here. So you can see that there's the OR intro, which takes A and turns that into A or B, and the OR intro 2, which takes B into A or B. So you have two constructors to do this. And you can also see that that's actually how it works. So if I try to prove A or B implies B or A, again I intro. So now I basically have, so the thing is, so I now know in my hypothesis A or B. So there are, given the way this works, there are two ways of getting to this. There are two ways I could have gotten to A or B. I could have gone there through OR intro 1, or I could have gotten there through OR intro 2. So what I do is I destruct it, and basically now it destructs this type, so the type for A or B, into its components. It takes its constructors and applies those in reverse in some sense. So it's telling me, okay, I've now got one goal, which is going from A to B or A, and it's also created a second goal, which I can show, which is going from B to B or A. So it basically tells me, okay, so the OR type has two constructors, just take both of them and turn both of them into goals. That's how the destruction works. And now, so if I have A, I now know that in order to create B or A, I've used the second constructor, basically. I've used OR intro 2, because going from A to B or A, that's the second constructor. So I use write, but this is basically, so write is basically saying second constructor. You can also say constructor 2. Write is a very specific tactic, because usually you use this for ORs, and left and right is of course the left and right side of the OR. Constructor 2, you go to A, and you apply that, and the same thing left. And now I've proved that the OR is immutative. This is sort of the basic way of proving sort of logical, and of course it gets much more complicated than this, because at some point you have all sorts of data structures working with natural numbers, for example, or all kinds of mathematical constructs. But this is more or less the basic logic, the basic way of proving statements in Coq. Now maybe I've got about 5 more minutes, so maybe a quick overview of how this actually works when you do programs. So just so there's an extension for, so this is again a simple program. So I've now written a function, so a recursive function, hence fixed point, div2, which basically takes a number and divides it by 2. So my first line is basically I integrate the specification into the type, so it takes n as input, a natural number. As output, it takes another natural number, x, with the property that either n is 2 times x, so my input is 2 times my output, or n is 2 times x plus 1. So basically, I divide using the sort of the integers, so I don't get a modulo. Well, so my program basically just matches n, and if it is the successor of the successor of p, so this is the piano definition of the natural numbers. So basically, if my natural number is 2 or higher, I just take I take div2p plus 1. So if it's a number 2, I just if the number is 2 or higher, I can just divide that number and take the successor of this. So and then otherwise I just return 0. So if it's 0 or 1, obviously I return 0. If it's 2, for example, I return 1. If it's 3, I again return 1, and so on and so forth. So I can, and now the nice thing about Coq is that now the way I've written this, hopefully, there you go. So the nice thing about this program extension is that it now actually automatically generates the proof obligations that I need to prove that this program actually satisfies the specification. So even if you're not convinced by my explanation just now, you can still, we're now going to prove that actually this program does what it's supposed to do. So you'll see that it's solving obligations automatically, and for the moment I've got 4 obligations remaining. So some of the more trivial obligations can actually be solved automatically by Coq, some of them can't. So let's look at obligation 1. Okay, so now I've got 2 natural numbers, p and x. So now I need to prove that if p is x plus 0, or p is x plus 0 plus 1, I now need to prove that p plus 2, so the successor of p, is the successor of x plus the successor of x plus 0, or the successor of p is the successor of x plus the successor of x plus 0 plus 1. Okay, so let's see how that works. So now here is where you start seeing the tactic language. So you can actually sort of make these things. So for example, my first term, I basically do exactly the same thing I do, because I've got an or in my hypothesis. So I'm basically going to do a case distinction on O. So I'll destruct O, and I just give my my 2 hypothesis names. So because if somebody changes the automatic name generation algorithm of Coq, my proof won't work anymore. So I now do that. So you'll see that now I've got, in this one, I've got a new hypothesis O, which is basically the left side of the OR. And in my second goal, I've got O1. So now I know that p is x plus 0. So I need to prove that the successor is successor. So now we can see that basically p is x plus 0. Well, then the successor of p has to be the successor of x. Sorry, the successor of x plus the successor of x. Because the plus 0 doesn't change anything. So we'll go for the left side. So now I actually need to. Oops. I'm just doing this step by step so it becomes slightly easier. So left. So I go through this. And now I just use the standard library of Coq, which has some information about the natural numbers, so you can look at this, print plus NSM. So if you look at this, basically plus NSM is a predefined theorem in the standard library of Coq somewhere that says the successor of N0 plus M is N0 plus the successor of M. So you can distribute the successor over addition. So if I rewrite this, you'll notice that I need to here. So you'll notice that the x plus the s x plus 0 now gets replaced by the s of x plus 0. Now, if you look at this bit and my hypothesis, you'll see that it tells me that p is equal to x plus 0. So why not use that? So I rewrite O, and again I need the dot here. And you'll see that, okay, so now it's replaced p on my screen by x plus 0. And now it's easy, because now here I've got the two parts of the equation are exactly the same, so I can just use the fact that equality is, yes, that's reflexive, and then basically reflexivity, oops, sorry, reflexivity, and there we go, I've now solved my obligation. So I've now solved this, I can say define, okay, so I've solved my obligation, now I need to go through the right turn. Basically there's a lot more, sort of I need to do some more things. But basically this is how it works for sort of a larger program, so you can integrate the specification into your program. Coq works out the proof obligation field automatically, some of them get solved automatically. Some of them you have to prove yourself, but at the end, so if you run this whole script, which you can see on your screen, it will tell you, yes, this is correct, and yes, you have solved your thing. Yeah.
May I ask like sort of about what's the most successful industrial application? What kind of businesses or software paradigms or development companies that sort of invest in Theorem?
I think that...
Maybe you'd like to repeat the question?
Yeah, sorry. So the question is basically, are there industrial applications for this, is sort of in a nutshell. So well, CompCert obviously is a big one. This is a research project, but this is a big secret part, because yeah, you want to do. I think that they've also got contacts with Airbus, the airline manufacturer, to sort of verify critical sections of airline software, which is also obviously a thing that you really want to be correct. But for the moment, it's kind of, yeah, those are the two I know of, and certainly CompCert and Airbus I'm not entirely sure about, but I think they've got stuff.
I would think of something that this can apply to, but I'm not sure if this is correct or wrong. In Agile, for example, with a test-driven development in DDD, would this be applicable? Because you're developing code and you want to test if the code is correct, but within the same programming language. Not sure if this would work or not.
Well, I think it all depends on. Well, I think they're kind of. From what I know about test-driven development, which isn't, I'm not a big expert on that, but you'd say that they're kind of two different things, in a sense that you could probably use the test-driven development to kind of identify the corner cases, the critical sections of your software, and then those would be the ones that you actually want to verify, because this takes, as you can see, even verifying very simple program actually takes quite a lot of effort. So if you can find some way to actually identify the critical sections and take those to take those to verify, and so you could sort of concentrate your manpower more efficiently, I would say. So maybe that's a way of doing it.
Any more questions?
Yes, one.
I think that, as you said before, that this language, this domain-specific language, should be used in baking compilers.
Yeah.
This,
Yeah, that's
and as well, for your question regarding test-driven development, I believe that we should not make this the mix between the theory itself and its specification. I think that the testing should be a unit testing function, for example, that access all the corner cases, as he said, but the main specification should be in a separate function. We should not mix this together as you did here.
okay. So, just out of curiosity, why do you think that?
Because they thought that this is the good practice to make the business logic in somewhere and the specification specification of this logic and
keep it
verifying it in unit testing separate functions.
Okay, yeah, it's a way of thinking. I mean, there's not, of course, there's nothing that keeps you from doing that. I mean, it's because in a certain sense, everything it's not an enormous distinction. The distinction between specification is a whole spectrum between specification and implementation. Your first specification would be something like, I want a program that does X, and then you write a more formal specification, and then you write a slightly more formal specification. So there will be this separation, will still be there, if you see my point. Because you have levels of specification to this. If you just use this for your latest level, so the really formal specification, you keep the slightly higher level design apart. Does that make sense?
Yes. A question here and then here.
Two questions. One, maybe I unfortunately lost this information. You represent some developers. Yes, it's some. You are one of author. What's the group?
No, I don't know. I'm not. I use it for to do formal verification. I'm not specifically a developer of it.
But who is developer? What is
So this is the INRIA in France, Rocancourt. So this is the group. They keep changing names. So I think last time I checked, they were called Proval. It's basically a research group in France that develops this.
And second question, maybe some comments or question to you. Do you agree that maybe such a type of it's not environment, and maybe it's not necessary to create environment, but this tool, let's say, maybe it's very, very important, such type of tool for system of artificial intelligence. It's all this logical manipulation, it's very important for further development within some artificial intelligence system, yes? Maybe it's not even so much for testing, it's like maybe one field. But mainly it can be very useful in the future for building more complex, of course.
I think any software that is mission critical, quote unquote, so where you really want to be sure that you want to have maximum confidence that your software actually obeys its specification, you can use this. So that goes for artificial intelligence, that goes for stuff we do, so communication or quantum processing.
But just such logical manipulation, yes, when you work with some senses, or it's exactly what we expect from system of artificial. It's for me, it's more or less clear.
No, that's absolutely. I mean, again, I'm probably not enough of an expert on artificial intelligence to really answer that question. But it sounds like a good development, certainly.
Something like data knowledge and such technology, because sometimes artificial intelligence include even some neural network. It's much more primitive. But I talk about some more global system and this kind of processing of logical essences, I can say.
I can see that working.
Because people always used to link, especially in Europe and also in Egypt, linking the logical programming and
Yes,
specifications to artificial intelligence, but actually
There is lots of resemblance between not exactly the syntax, the logic of this to the original.
prologue and logic programming. Well, it is a logic programming anyway, so
Just the same thing. Maybe prologue goes backward, while it's.
not really,
it's
prologue
great
is
to
still
be
under
able
use. Actually, it's used in companies now. It's used in many companies for industrial.
See, and still also I see that Z is more expressive.
I mean, of course, don't forget that what I showed here are very simple examples. I mean, it becomes a lot more complicated as it goes on.
No, I'm talking about the syntax.
Okay, yeah.
Expressions, identify the inputs and outputs, identify the mappings. They have very good mechanism to express semantics,
Mm.
not just syntax.
Which is logic.
Yeah, so that's a slightly higher level.
Yes.
That's how you can
But it
verify.
makes sense actually that use proof of specification in safety critical.
Exactly.
Yeah,
That's
so it
where
makes sense that you use
that's where
the
it is.
airlines or something.
And now the
Not
timekeeper.
necessarily for the whole airline system.
The
Just
Just
the
for
critical.
finance. I hope that you don't get offended, depressed because of the comments. Actually,
that's
the
all
field
right.
is far away from ours, so we are really
No,
sorry for
that's-
this.
yeah.
Especially mine.
Questions are always fine, that's not a problem, of course not. No.
Okay, so can we have actually the questions means that they were awake after the break, so this is good.
That's
They are asking questions.
lots
So
of questions always
on
good.
behalf of the project,
Thank you very much.
I would like to thank you very much. Yeah, picture,
Oh,
with the name of the project. This is the project. Okay, thank you.
Excellent, thank you very much.
Thank you very much. Thank you. Thank you.
Okay,
And,
we need to
Yeah.
go back to